All right, so in our last activity, 3.3.2, we saw that the absolute min and max was actually not only controlled by the critical points of the function, but it was actually controlled also by the interval that we took the function on, meaning the highest point for x and the lowest point for x. So, and you guys saw that as we changed the interval around, that changed what the absolute maximum and the absolute minimum was most of the time. So all we're going to do right now is we're going to put a name to it, and that name is called the extreme value theorem. So if f is continuous, notice don't glance over this. Every time we use like a mean value theorem or extreme value theorem or the IVT, the intermediate value theorem, we're going to have to say something before it. We're going to have to make sure that the function can even be used. So the thing that we're going to have to look for is continuity. If f is continuous, meaning that it's nice and smooth, has no holes, if f is a continuous function on a closed interval from a to b, then f attains both an absolute minimum and an absolute maximum. So it has to. If you think about, if you take a function, you cut it up, you have a low point and a high point, you're going to have an absolute minimum and an absolute maximum. And that minimum and maximum is going to change depending on the interval that you take. So here's kind of that brass tacks, the stuff that you should definitely write down. That you were going to use all the time. To find the absolute maximum or minimum of a continuous function f on an interval from a to b, here's your first step. Find all the critical numbers on f that lie in that interval. Sometimes those critical numbers will be in the interval. Sometimes they won't be in the interval and you won't have to worry about them. Evaluate the function f at each critical number in the interval and at each endpoint of the interval. So we did this in class with our last activity. We called it a candidate table, evaluating the function not only at those critical points, but also at the endpoints. And then from there, you can go ahead and you can pick the smallest of those. That will be the absolute minimum. And then you can go ahead and you can pick the largest of those, and that's going to be the absolute maximum. So like we were talking about before, sometimes, actually most of the time, the function itself will create a maximum min, but the interval will also create a maximum min. So if you look at our first interval, these are all the same function, is between -2 and 3. So we have 1, 2 critical numbers. This critical number actually looks like it's going to be our absolute minimum because it's the lowest value on the interval. This number would typically be a maximum, but this one's only a relative maximum because this endpoint over here actually has a bigger y value, a y value that's farther away from 0. If we change the interval now, so notice we changed the interval, both critical points are still in the interval. Now all of a sudden this point right here at, I think it was √2, yeah, something √2, whatever the y value was, this is going to be your absolute minimum, and this critical point is actually going to be your absolute maximum because it's the highest point. And then finally, if we change the interval again, we make the closed interval between -2 and 1. That's going to change the minimum, and it's going to change the maximum as well. So the minimum, notice, isn't going to be this critical point. The absolute minimum is going to be the end of that interval, and the absolute maximum is going to be the critical point. So, big picture stuff, the interval matters. Make sure that not only do you check the critical points, giving you relative maxes and mins, you also now have to check the endpoints of your interval to make sure that they're maxes and mins for real. All right, kept it under 5. Peace.